This over-identification test will be solved without using linear algebra at all, right? So the setup is pretty simple. It's simplified to solve without linear algebra. So first, there is only one demeaned scalar regressor, and one IV is certainly valid, but the other IV, Z2, is uncertain whether it is valid or not. So, and then we are first we'll consider unrestricted model. Unrestricted model does not utilize the hypothesis to your estimation. So it is only using the certainly valid instrument only. That means there is only one instrument for one endogenous variable. So it is exact identification case. But restricted model utilizes the uncertain hypothesis, right? So hypothesis, the Z2 is assumed to be valid. And in this case, you have over-identification because you have two instruments for one endogenous variable. We studied what happens that in that case in the previous chapter. Okay, let's first think about the unrestricted model. Just notations. The moment function is like this. Okay, but later you must be familiar with this notation and manipulation. Sample moment will be denoted this way. U, of course, stands for unrestricted model. And then in this case, the weighting matrix does not matter because it is one-to-one, right? One IV to one instrument, one endogenous variable. So no matter what weighting matrix you use, the result does not change. So I will just use identity matrix as a weighting matrix, right? So pretty simple. And as you see, when you use identity matrix, this is just basically Euclidean norm, right? Euclidean norm squared. So later we are going to see that. And then you are going to minimize that Euclidean norm. And I want to show that this is 0, but that is equivalent to showing this. Intuition is clear here. You have one parameter for one moment condition, so you can satisfy that. It is exactly satisfied. Proof is like this. So we will think about the first order condition where H, so in our lecture note, we usually write capital G, but for minimize the confusion, G is already here. So we are going to use H instead. H is this function, which is basically derivative, okay? So the first order condition looks like this in general, right? So in general, in our lecture note, we learned the first order condition takes this form. This was the first order condition, but now W is identity, W is gone, and also actually H is, so G is replaced by H1. It is scalar, right? You may just think it as G hat UN is 0 divided by H1, right? If H is not 0. So if you show that H1 is not 0, then of course this should be 0 for this to be true, right? So we have to make sure this is not 0. That is from the relevance condition. So this is sample covariance because X is demeaned. Sample covariance between X and Z1 is non-zero in the limit, right? Because its limit is not 0, right? So H1 hat converges to H that is not 0. So then if n is large enough, then in the end it will be different from 0. So that shows H1 is not 0, so it is 0. Idea is pretty simple, and it holds whenever the number of IV number of moment conditions equals the number of parameters. Now let's go to the troublesome part. So the restricted model is crazy. It's crazy difficult. We are going to define some notation again. So there are two moments. Now moment is two-dimensional vector. And H also different, h1 and h2, and everything is scalar, like each notation is scalar, each alphabet is scalar. Then let's think about the restricted estimator. The sample criterion function should look like this in general. Now the weighting matrix matters, right? Because there are two instruments for one parameter. So depending on your weighting matrix, your result, your estimator may be different. That is a problem. So weighting matrix defined this way, and I'll just start from the optimal weighting matrix, and later I will change it to the identity by the assumption. So by the way, let's think about it. Like, we know we need to show that something goes to chi-square. Okay, then what is chi-square? Chi-square in general looks like this. Suppose a vector q by 1 vector converges to normal distribution with variance omega, and then its quadratic form x prime omega inverse x converges to chi-square q. Okay, then we have pretty similar form. So split n into square root n here and square root n here, then something transpose omega inverse something, right? Exactly same form, right? So the only difference here is, and additionally, we know we have some normal distribution, right? So the sample moment converges to normal distribution. That is also nice. The problem here is we have different degrees of freedom, right? According to this general result, the degrees of freedom q should be the dimension of the vector, right? That should be 2 in our case, but we know f-test or chi-square test, this degrees of freedom is the difference between the number of moment conditions minus the number of parameters, right? It is 1. The reason why they are different is because we have different argument, right? In our theory, we considered beta 0, so unknown but fixed true parameter. But in our practice, in our test, we are going to use the estimator, right? So in undergrad class, I explain it like this. So before calculating this chi-square test statistic, you have to calculate the estimator first. So you are losing 1 degree of freedom. That is approximate, roughly, right? So let me explain why. So that is because G hat, the moment is 2 dimension, but those two moments are perfectly correlated because of the first order condition, right? So this is the first order condition. In general, the first order condition looked like this. This was the notation we had in the GMM chapter. Anyhow, this is the first order condition that can be written this way. So I'm going to use the assumption here, right? So I'd like to ignore the weighting matrix for algebra, right? So I'm going to assume that the weighting matrix should be in the identity. And then in that case, the first order condition implies this result. That means two sample moments are actually perfectly correlated, right? So for example, so suppose that H1 and H2 are both positive. That means if G1 is negative, then G2 should be positive and multiplied by a certain number. So it's linear dependence, right? So the second moment is just something multiplied to the first moment. So even if we have, it looks like 2 dimensions, but actually it looks like 2 dimensions, but actually it is just 1, right? So the two things are basically one information, right? Linear dependence, the rank is only 1. Now then, how can we show that? So then we are going to delete G2, right? The criterion function, we are going to show that this converges to chi-square. So in our notation, we can write this in this way. But as I said, we are going to delete this guy. So G2 is just following G1, perfectly correlated with G1. So I will utilize this into here, and then you are going to get just one random variable, right? Just some constant, something multiplied to this guy, right? And it will become like this. Okay, now then I am going to write it this way, say, so this will be x transpose omega inverse x. If x is scalar, it will become x squared times omega over omega. It will go to chi-square 1, right? So I will show that here this is x and this is omega 1 over omega, right? So what I have to show here is x converges to normal distribution 0 omega. Then we have that. We have desired result. This is the desired result. So we have to show this, then we have the desired result. Let's show this. Still it is not easy. Still it is not easy because the sample moment involves estimator. Estimator itself is also random. Sample moment is random. Estimator is also random. Then the problem there is their covariance. They are correlated. So we utilize the influence function now. Remember, influence function in general was so this was the influence function in GMM. So we are going to follow the same rule, and we get this. And of course, omega will be simplified, and H is just two-dimensional. So if you do the algebra, so it's just 2x2 matrix algebra. So this is really annoying, but I did it. This part will become the denominator. It is actually scalar, right? H prime H is scalar, so it goes to denominator. And H is H1 and H2, so H1 times this, H2 times this. So it is linear form of like these two random things, right? So random error, estimation error is following from two different like moments, sample moments, okay? So then, and they will be now go back to the sample moment. Sample moment looks like this. So, right, this is just definition. What I'm going to do here is y can be written in this way, okay? So u will just be separated, but what I'm going to do here is beta 0 and beta hat will be bundled because we are going to imply we are going to use the influence function. Use the influence function here, right? You use the influence function here, and then plug influence function here and rearrange. Then you will get this guy, right? So you have to. This is the sample moment, right? Remember, our goal is to show this. So we want to show that the first sample moment has asymptotic variance of this form. Then what you can learn from here, we know this part after multiplying square root n, if you multiply square root n, then this guy and this guy will be normally distributed, right? So we have to find the variance. But to do that, we have to think about their covariance again. They are correlated. How to do that? As a vector, they converge to normal distribution, standard normal distribution, because we assumed omega is identity. So here, originally, you have to have omega here, but we assumed that equals identity. And then, if you multiply, say, x converges to normal distribution 0 and omega, and if you multiply a vector, say, A transpose x, then it converges to normal distribution A transpose omega A, right? So that means here, if you multiply A1 and A2 transpose in here, then you will get this form. And A transpose identity A will become this, right? And then this is exactly same structure as this. This is A1. This is A1. This is A2. So calculate A1 squared plus A2 squared, then you will get the desired result, right? The desired result is this, right? So your proof is done. This is how we prove chi-square. It is crazy because we did not use linear algebra. So I explained diagonalization in class, so that will simplify the algebra a lot.